The universe is vast. It's a canvas of unimaginable size and wonder. Recent discoveries in space science have brought us closer than ever to answering one of humanity's oldest questions. Are we alone? The search for extraterrestrial life, once relegated to the realms of science fiction, is now a serious scientific endeavor fueled by tantalizing clues and groundbreaking technologies. For millennia, we gazed upon the stars with a mixture of awe and uncertainty. Were those distant points of light home to other beings, perhaps even civilizations far more advanced than our own? The possibility, while exhilarating, seemed hopelessly out of reach. How could we ever hope to bridge the unfathomable gulfs of space to find out? Today, our understanding of the cosmos is undergoing a revolution. Powerful telescopes, both on Earth and in space, are peering into the depths of the universe, revealing its secrets with unprecedented clarity. We are discovering planets around other stars, worlds that may harbor the conditions necessary for life as we know it, or perhaps something even more extraordinary. The evidence, while still circumstantial, is mounting, pointing towards a universe teeming with possibilities. This is a thrilling time to be alive, a time when the dream of finding alien life is edging closer to reality. Join me as we embark on a journey to explore the latest discoveries, unravel the mysteries, and contemplate the profound implications of finding that we are not alone in the universe. Our search for alien life begins with a hunt for planets beyond our solar system, planets we call exoplanets. These celestial wanderers, once hidden from our view, are now being discovered at an astonishing rate, thanks to ingenious detection methods and advances in telescope technology. Each new discovery adds another piece to the puzzle, helping us to understand the diversity of worlds that exist in our galaxy. One of the most successful techniques for finding exoplanets is the transit method. This involves observing a star for a telltale dip in its brightness, a sign that a planet is passing in front of it, blocking a tiny fraction of its light. By analyzing these dips, astronomers can determine the size of the planet and its distance from its host star. Another powerful method is the radial velocity method, which looks for the subtle wobble of a star caused by the gravitational pull of an orbiting planet. This wobble creates a Doppler shift in the star's light, stretching or compressing the wavelength depending on whether the star is moving towards or away from us. By measuring these shifts, astronomers can infer the mass of the planet and its orbital period. These methods, along with others, have revealed a staggering diversity of exoplanets, from gas giants larger than Jupiter to rocky worlds similar in size to Earth. Some orbit their stars closely, bathed in intense heat, while others circle at frigid distances. Some are part of multi-planet systems engaged in a delicate gravitational dance, while others wander alone through the vastness of space.
Our search for extraterrestrial life is not limited to planets that resemble our own. In fact, some of the most promising places to look may be the most extreme environments imaginable. On Earth, we have discovered organisms known as extremophiles that thrive in conditions once thought impossible for life to exist. These hardy creatures challenge our assumptions about what life needs to survive and expand the possibilities for where we might find it elsewhere in the universe. From the scalding heat of volcanic vents to the crushing pressure of the deep ocean, from the icy plains of Antarctica to the highly acidic waters of toxic lakes, extremophiles have found a way to make a living in the most inhospitable corners of our planet. They have evolved unique adaptations that allow them to withstand extremes of temperature, pressure, pH, radiation, and even the absence of sunlight. Take, for example, the tardigrades, also known as water bears or moss piglets. These microscopic creatures are renowned for their resilience, able to survive being frozen, boiled, dried, exposed to the vacuum of space, and even blasted with radiation that would kill a human 1,000 times over. Their secret lies in their ability to enter a state of suspended animation, slowing their metabolism to a near standstill until conditions improve. Then there are the chemoautotrophs, organisms that live deep beneath the Earth's surface, far from the reach of sunlight. Instead of photosynthesis, these remarkable life forms obtain energy from chemical reactions, such as the oxidation of iron or sulfur compounds. They demonstrate that life can exist even in the absence of an external energy source like the sun.
Section 4. Water worlds Enceladus, Europa, and the search for subsurface oceans. In our search for alien life, water is considered a key ingredient. Where there's water, there's a potential for life as we know it. While liquid water is scarce on the surfaces of most planets and moons in our solar system, there are some intriguing exceptions, places where vast oceans are thought to exist hidden beneath layers of ice. These subsurface oceans, shielded from the harsh conditions of space, could provide stable environments for life to evolve and flourish. One such place is Enceladus, a small icy moon of Saturn. In 2005, the Cassini spacecraft discovered plumes of water vapor spewing from cracks in Enceladus's south polar region. These geysers, erupting hundreds of kilometers into space, are thought to originate from a vast subsurface ocean, warmed by tidal forces from Saturn and its other moons. Analysis of the plumes has revealed the presence of organic molecules, the building blocks of life, further raising hopes that Enceladus could harbor microbial life. Another promising candidate is Europa, one of Jupiter's 4 largest moons. Europa's surface is covered in a thick layer of ice, but beneath this icy shell, scientists believe there is a global ocean of liquid water, perhaps twice the volume of all the Earth's oceans combined. This ocean is thought to be salty and potentially rich in minerals, making it a prime candidate for life. NASA's Europa Clipper mission, scheduled to launch in 2024, will study Europa in detail, searching for signs of life in its subsurface ocean.
Section 5. The Red Planet Secrets. Methane on Mars and the hunt for microbial Martians. Mars, our rusty red neighbor, has long captured the human imagination as a potential abode for life. While the planet's surface is now a cold, dry desert, evidence suggests that Mars was once a much warmer and wetter place, with rivers, lakes, and perhaps even oceans. If life ever arose on Mars, it's possible that it could still be clinging to existence beneath the planet's surface, where water ice and even liquid water may still exist. One of the most intriguing pieces of evidence for life on Mars is the presence of methane in the planet's atmosphere. Methane is a gas that can be produced by both geological and biological processes. On Earth, the vast majority of methane is produced by living organisms, so its presence on Mars raises the tantalizing possibility that it too could be a sign of life. The Curiosity rover, which has been exploring Gale Crater on Mars since 2012, has detected methane in the Martian atmosphere on several occasions. These methane spikes, as they are known, are transient and localized, suggesting that they are being released from specific sources on or beneath the surface. While the origin of this methane is still a mystery, its presence is a compelling clue that Mars may not be as dead as it seems.
Section 6. Life but not as we know it. Imagining non-carbon-based life forms. In our search for extraterrestrial life, we often focus on finding life as we know it. Life that is carbon-based and requires water as a solvent. But what if life elsewhere in the universe has taken a different path? What if there are life forms that are not carbon-based? Life forms that rely on different chemical elements and solvents to carry out the essential functions of life. The possibility of non-carbon-based life is not as far-fetched as it may seem. Carbon is a versatile element, but it is not the only one capable of forming complex molecules. Silicon, for example, is located just below carbon on the periodic table and shares many of its chemical properties. Silicon-based life forms could potentially exist in environments that are too hot or too acidic for carbon-based life. Other elements, such as nitrogen, phosphorus, and sulfur, could also play a role in non-carbon-based life. These elements are essential for life as we know it, and they could potentially form the basis for alternative biochemistries. For example, some scientists have speculated